All right, so our titration is plugging along. We had 25 milliliters of this formic acid floating around in a flask. And then we've added 5 milliliters of this strong base as a titrant. So in solution right now, we're going to talk about this quick since we just said all the words. We have 30 milliliters total. We had the 25, we've added 5, so there's 30 milliliters total. We'll have to come back to this in a minute. Now, balanced chemical equation. What is actually happening? Well, we have the formic acid. We're going to add to that some OH minus anions, and we don't care about the counter ion. It's a spectator ion, so I just left it off, and that's okay. When that hydroxide picks up a proton, it forms a water and a conjugate base, and it forms those in a 1-to-1 ratio. Now, what's happening? Well, we have 2 species, and we have an initial amount of 2 species, which is strong base and weak acid. So we need to take both of those into account, and we're talking about things reacting with one another. And so we can't really talk about concentrations anymore. We got to talk about moles. So we're going to have to take a minute, figure out the moles of HCOOH, and then figure out the moles of NaOH. You have both a volume and a concentration of the base. You have both a volume and a concentration of the acid. So do some magic with both of those things and then figure out the number of moles. You should get numbers that look at least somewhat like mine. Looks kind of like that there. Now this is initially. And initially we still don't have anything over here, and we're not going to care about that water. Okay? What is the change? Well, what's happening in the reaction? As you add this strong base, every time you add a mole of strong base, it's going to react with a mole of the weak acid every time. And so it is going to be consumed and it's going to disappear every time. And every time it disappears, it does so by taking away a mole of weak acid. And every time a mole of weak acid is taken away, a mole of that conjugate base is formed. Every time, without fail. So our change line is just like it was before, only instead of X, we have an actual value. Because at the end of the day, at least up until the equivalence point, we should end up with 0 moles of that strong base, because it should be converting the weak acid to the conjugate base. Now, once all that reaction has happened, I end up with 1.75 times 10 to the minus 3 moles of that weak acid, and I end up with 7.5 times 10 to the minus 4 moles of that conjugate base. Now, I'm still not in terms of molarity, and if it makes you feel better, you could go through and you could divide both of the moles of conjugate acid and conjugate base by 0.03 liters, and you could come up with some concentrations. But I am not going to worry about it, because my Henderson-Hasselbalch equation has these guys, and it has these guys in terms of a ratio. That ratio would have the same conversion factor in the numerator and the denominator, and as such, I really don't need to perform it. So I'm not going to go to molarity. I'm going to leave everything in moles. Sorry, I accidentally went backwards for a minute. So as I redo this, I'm going to say that the pH is equal to the pKa, which I don't have, but I do have the Ka. So I can say the negative log of 1.8 times 10 to the minus 4. 1.8 times 10 to the minus 4. It just came from the problem. And I can say I have the log of the conjugate base, or 7.5 times 10 to the minus 4 over the conjugate acid, which is 1.75 times 10 to the minus 3. Plugging that into the calculator, I get a pH of 3.37. Now I have added strong base to a weak acid, so I should go up in pH. I should still be acidic though, because I'm in the buffer region, and if I look compared to my original pH, I am more basic, but I'm still in the acidic region because it is acting as a buffer. So this looks like a perfectly reasonable pH.